Hello, so in this research log, I will be discussing a method for targeting Alzheimer's, which is different than the treehouse delivery method, which I talked about in other research logs. Also with me today are my assistants in science, Varshith, Chekka, and Aryan.
Okay. Hi, my name is Aryan Chadha.
And I'm Varshith Chekka.
And today we're going to be discussing the cellular cause of Alzheimer's disease. As you can see, this is a cell membrane of a brain cell, or more known as a neuron. There's something particularly weird about this cell membrane because it has a protein called APP, or amyloid precursor protein. On this amyloid precursor protein, or APP, has to be broken down by enzymes, so it can become soluble and help the body. But, these are the enzymes. The first enzyme is the gamma enzyme, which is near the bottom. The second enzyme is the alpha enzyme, which is near basically the top. There's one other enzyme which is harmful to the body and associated with Alzheimer's disease, which is the beta enzyme. When paired with the alpha enzyme, the beta enzyme can break off the protein, the APP, and become a sticky, non-soluble mess known as the amyloid beta. When the amyloid beta is made, there become more amyloid betas, and they get sticky and clumped together. When they get sticky and clumped together, they inhibit neurotransmitters, so the neurotransmitters can't talk to each other, and that is associated with memory loss. This is the main cause of Alzheimer's disease.
Yeah, we did it, man.
Alright, so where we left off was that there is no conduction between the receptor and the transmitter, so the neurotransmitters aren't getting across like they should be. So how can you counter this? Well, first, let's look at what's blocking it. So let's say these magnets are plaques. These plaques are blocking reception. We need a way to get around. So what are some good conductors that we know of that are compact and can conduct electric signals? Well, the first thing that comes to mind with modern nanotechnology is graphene. But the problem with graphene is that it doesn't go along with any current diagnosis methods that we know of to this day. So let's discuss some diagnosis methods, invasive and non-invasive. So starting with the non-invasive diagnosis methods, the most eminent one in today's technology is a computer system. And this is a very complex computer system, but I will be simplifying what goes on in it. So there's your input box, there's your output box, and between is a bunch of core boxes, not just two like I drew, but many core boxes which analyze different problems that occur during Alzheimer's, such as atrophy in the brain. Another problem is loss of intelligence or memory, which can occur in the frontal lobe. So we'll have a box analyze the frontal lobe, and we'll have one analyze the parietal lobe. And really, there are many more components to this, but we'll just simplify it here for a moment. So, as each box analyzes each part, it remembers what it's analyzing. And as future diagnoses occur, it's much quicker, a much faster diagnosis, because there have already been so many inputs that it remembers what's going on. And this is known as a computer that utilizes deep learning. And I have discussed this in previous research logs, but a computer that uses deep learning essentially is a very complex computer, often a quantum computer, but it is also very expensive and is still in developmental stages right now. So we want something that's much cheaper and goes along with technology that we do actually have fully developed today that we can be sure of. I'm not saying that we can't be sure of deep learning computers, but I am saying that it is not at its full potential. So now let's look at invasive methods, because this is the best non-invasive method we have at the moment. So Krithan Nithyanandam came up with this method, which is actually a very genius method, of using quantum dots to get through the blood-brain barrier, which is a barrier which blocks off substances which are not needed in the brain. It gets through this barrier, we'll call it B for blood-brain barrier, and it gets to these receptor and transmission nodes. And basically what a quantum dot is a semiconductor material that has electrons or holes or excitons, which are combinations of electrons and holes, sort of squished up trapped inside of it. And this works, but once this semiconductor material has reached the inside, then this quantum dot can determine what's going on based on different spectroscopies that are used when in the brain, such as functional NIR spectroscopy, which analyzes the functions of something through a near-infrared range. So with this FNIR, you get different band gaps, different, not really colors, but with photoelectric spectra, it technically turns out to be a range of different emissions of parts of the electromagnetic spectrum. So use FNIR spectroscopy, or functional near-infrared spectroscopy, to analyze the activity that is going on in this zone. But the analysis is what has been come up to this day. While this is being analyzed, you can prescribe antibiotics such as donepezil or other treatment methods such as the trehalose delivery method, but it won't really help you very much because these things take a long time these things are long-term solutions, and donepezil doesn't even have a very high guarantee of actually working. And in some studies, it was also found that it is not completely known which stage donepezil actually works in. And donepezil is the main medicine prescribed for Alzheimer's. So obviously, there is need for a better prescription and also a better method in general. So how can you combine diagnosis with prescription and essentially targeting the end of Alzheimer's? Well, remember how I mentioned graphene earlier? That could just be the trick. So graphene, even though it's not a semiconductor, has the ability to squeeze the excitons and the electrons, valence electrons, and valence holes, valence band holes, into it. But there is a slight problem. Graphene doesn't really have any smooth surfaces, which causes flaking, breaks in the middle of the graphene body, which lets go of the electrons. The electrons escape. So what is a good way to keep the electrons in but still keep it together with the graphene? Well, what is used a lot in studies is using both electric and magnetic fields. If just the electric field is used, then this flaking effect with the graphene would still sort of occur. So electric and magnetic fields, and when is this used very often? Magnetic resonance imaging. Also, electric fields are used in our day-to-day lives, such as when we are charging our smartphones. So, by using a combination of MRI and electric field, we can essentially keep graphene holding these valence band electrons, valence band holes, and excitons. We can take it to the transmission and receptor area between neurons, where these plaques are found. This graphene can connect to the outsides and continue transmission, which essentially will get signals flowing again. And the diagnosis can still occur because the quantum dot, as Krithun Nathayananda mentioned, can still diagnose it. Now, you're probably thinking, if we haven't diagnosed it yet, why would this graphene implementation be helpful? We don't even know whether or not they have Alzheimer's. Well, in general, one in three senior citizens in America die of Alzheimer's, and that is actually a very high percentage. So any senior citizen should have some sort of device implanted between neurons that will enable their cognitive abilities and intelligence, etc., to be enhanced, because they have already been deteriorated by aging. Now, in younger patients, this may not be necessary, but it is still a good idea because most diagnosis of Alzheimer's still occurs through opinionative reasoning. By this, I mean that doctors view symptoms just through basic observations, such as memory loss, in the way that people can't remember names, or can't recall words, or can't think abstractly. So, when doctors diagnose it in this way, and it seems quite likely that one has Alzheimer's, then the graphene squeezing the quantum dots can be diagnosed. Now, it seems like, there are 100 billion neurons in the brain. So how will we send this many strands of quantum dots and graphene into the brain? Now you have to understand this graphene is also very small. So it can easily be sent into the brain in small fragments through some sort of liquid carrier, or just through some sort of shot that passes through the blood-brain barrier when injected. So this is one of the easiest methods, and so this is one of the best methods, especially with senior citizens, for targeting Alzheimer's, and it is not a method on which much research exists, because graphene is a very recent material. Graphene was only obtained in 2010, and the people who obtained it won the Nobel Peace Prize for it. So it's a very recent nano material. And also, quantum dot diagnosis was not brought up until a year or two ago. So this is also very new. So combining these ideas can be a very big step in targeting Alzheimer's for us.